You are standing on a planet that feels impossibly large. A world with oceans so wide that crossing them once took months of dangerous sailing. A world with continents so vast that entire civilizations can rise and fall without ever reaching the edges of them. To the human body, Earth feels enormous. But that feeling is an illusion created by scale. Because the moment we begin measuring this planet against the objects that surround it in space, something unsettling happens. The world beneath your feet begins to shrink, and it never stops shrinking. Visual, Earth slowly rotating in darkness. Earth has a circumference of about 40,075 kilometers, roughly 24,900 miles around the equator. That is a real number, a number confirmed by satellites, navigation systems, and centuries of measurement. But numbers alone rarely make distance meaningful. So let's turn that number into something physical. And imagine boarding a commercial jet flying at about 900 kilometers per hour, roughly 550 miles per hour. Now imagine that plane never lands, no refueling stops, no waiting for air traffic clearance, no storms to avoid. Just a perfectly straight path around the planet. At that speed, it would take about 45 hours to circle the entire Earth, almost 2 full days of continuous flight. And that's just to return to where you started. And now imagine making the same journey in a car, driving at 110 kilometers per hour, about 70 miles per hour, on an impossibly straight highway that wraps perfectly around the equator. That drive would take more than 2 weeks. 14 days of non-stop driving. No sleep, no fuel stops, no traffic. Just driving, endlessly, until you return to the same point on the planet. At human scale, Earth is truly enormous, and that makes sense. But because the human body evolved to move at about 5 kilometers per hour, roughly 3 miles per hour. For most of our species' history, the fastest way to travel was simply walking. When early humans began migrating out of Africa around 70,000 years ago, the journey to the southern tip of South America took roughly 10,000 years of gradual migration across generations. 10,000 years, just to cross a fraction of the surface of this planet. From the perspective of human biology, Earth is massive, but now we zoom out, and the illusion begins to break. Visual, camera slowly pulling away from Earth. The deepest place in Earth's oceans is the Challenger Deep in the Mariana Trench. Its depth reaches about 11 kilometers, roughly 36,000 feet below sea level. At that depth, the pressure exceeds 1,000 times the atmospheric pressure at the surface. The environment is completely dark. Sunlight disappears after the first kilometer of water. Now, below that point, the ocean exists in permanent night. Fewer than 30 people in human history have ever visited the bottom of the Mariana Trench. Each descent required specially engineered submersibles built from thick titanium pressure hulls designed to withstand forces powerful enough to crush most vehicles instantly. Reaching that depth is one of the most extreme journeys humans have ever attempted on this planet. It feels like exploring another world. But here is the number that changes everything. Earth's diameter is about 12,742 kilometers, roughly 7,918 miles, which means the deepest trench on Earth is less than 11 kilometers deep, a tiny scratch on a sphere nearly 13,000 kilometers across. Let's turn that into something you can touch. Imagine shrinking Earth down to the size of a basketball. At that scale, the Mariana Trench, the deepest place in the entire ocean, would be so shallow that you couldn't feel it with your fingertips. Run your hand across the surface of that basketball. It would feel perfectly smooth. The deepest scar on our planet would disappear entirely. The enormous trench that challenges our engineering and threatens human survival becomes invisible. This is the first lesson of cosmic scale. Things that feel enormous up close often become almost nothing when viewed from just one level higher, and this pattern repeats again and again and again. Now we take the next step, because Earth is not alone. Our planet orbits a star that immediately destroys any remaining sense of planetary scale. Visual: Earth orbiting the Sun. The average distance between Earth and the Sun is about 150 million kilometers, roughly 93 million miles. Astronomers call this distance 1 astronomical unit, or 1 astronomical unit. It's the basic measuring stick for distances within the solar system. But once again, numbers alone don't mean much. So let's translate that distance into something our brains can attempt to grasp. If you could somehow travel to the Sun in a commercial airplane flying at 900 kilometers per hour, the journey would take nearly 19 years. 19 years of continuous flight, no stopping, no landing, and just flying towards the Sun. At the speed of a rifle bullet, roughly 2,700 kilometers per hour, the trip would still take more than 6 years. 6 years, at bullet speed, even light, the fastest thing that exists in the universe, requires time to cross this distance. Light travels at about 300,000 kilometers per second. At that incredible speed, sunlight takes about 8 minutes and 20 seconds to reach Earth, which means the sunlight warming your skin right now left the surface of the Sun more than 8 minutes ago. If the Sun were to disappear this instant, we would not know for over 8 minutes. The sky would still be bright. The warmth would still reach the ground. Life on Earth would continue as if nothing had happened for 8 minutes. That is how far away our own star is. But distance is only half the story, because the Sun itself is enormous, far larger than anything the human mind naturally expects. Visual: Earth compared to the Sun. The Sun has a diameter of about 1.39 million kilometers. That makes it roughly 109 times wider than Earth. If you lined up 109 Earths side by side, they would stretch across the face of the Sun. But volume is where the numbers become truly absurd. About 1.3 million Earths could fit inside the Sun. Not beside it, inside it. Imagine every mountain range, every ocean, every forest, every city, replicated 1.3 million times. All of it could fit inside our star. The object rising in the sky every morning is not a small glowing disk. It is a colossal sphere of nuclear fire. A fusion reactor converting about 4 million tons of matter into energy every second. Every second. That energy travels across 150 million kilometers of space and reaches the planet where you are standing. And here is the detail that makes this even more humbling. And the Sun contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of cosmic dust, all of it combined accounts for less than 0.14%. Earth is not a central object in this system. It is a tiny passenger orbiting an enormous nuclear engine. But even the Sun, a star capable of swallowing more than 1 million Earths, is not the largest thing in our cosmic neighborhood. Not even close, because the solar system itself stretches far beyond the orbit of our planet, far beyond the orbit of Mars, far beyond the orbit of the giant planets, into distances so vast that the emptiness between objects becomes the defining feature of the entire system. And once we begin measuring those distances, Earth disappears completely. If this shift in scale is already starting to feel unsettling, then you're going to enjoy what comes next. Because in the next step of this journey, we leave Earth behind entirely. We cross the solar system. We encounter distances so large that even light begins to feel slow. and we discover something surprising about the space between the planets. It is not filled with objects. It is filled with nothing. If exploring the deep history and scale of the universe fascinates you, consider subscribing to If Earth Had a Past, because this journey has only just begun. The planets of our solar system feel familiar. Mercury, Venus, Earth, Mars. Then the giants: Jupiter, Saturn, Uranus, Neptune. In textbooks and diagrams, they often appear neatly arranged, close together, almost touching. But those images are lies of convenience. They compress distances that are almost impossible for the human brain to grasp. Because the defining feature of the solar system is not the planets, it is the emptiness between them. And visual, solar system diagram stretching outward. Earth orbits the Sun at an average distance of about 150 million kilometers, roughly 93 million miles. That distance is called 1 astronomical unit, or 1 astronomical unit. It's the baseline astronomers use to measure everything else in our solar system. Mars, the next planet outward, sits about 1.5 astronomical units from the Sun. Jupiter, the giant of the planetary family, orbits at roughly 5 astronomical units. Saturn drifts even farther out at about 9.5 astronomical units. And Neptune, the most distant major planet, circles the Sun nearly 30 astronomical units away. That is about 4.5 billion kilometers from the center of the solar system. To understand what that distance really means, imagine a beam of light leaving the Sun. Light travels faster than anything else in the universe. Nothing can move faster. And yet, even light requires time. From the Sun to Earth, light takes about 8 minutes and 20 seconds. From the Sun to Neptune, the journey takes more than 4 hours. 4 hours of travel, at the absolute speed limit of the universe. Now imagine communication across those distances. A spacecraft operating near Neptune cannot talk to Earth in real time. If something goes wrong and the spacecraft sends a distress signal, the message requires 4 hours to reach mission control. And any response from Earth takes another 4 hours to travel back. That means a full conversation across the solar system takes 8 hours. In practical terms, a spacecraft that far away is completely on its own. And that's not hypothetical. Humanity has already experienced it. Visual: Voyager spacecraft drifting through space. In 1977, NASA launched 2 small robotic explorers, Voyager 1 and Voyager 2. Their mission was simple in concept, but extraordinary in execution. Fly past the outer planets, send back images, and then continue outward into deep space. Voyager 1 is now the most distant human-made object in existence. After nearly 5 decades of travel, it has reached a distance of about 24 billion kilometers from Earth. That is roughly 15 billion miles. It sounds enormous, but in cosmic terms, Voyager has barely left home. Voyager 1 travels through space at about 17 kilometers per second. That's around 61,000 kilometers per hour, or roughly 38,000 miles per hour. Faster than any vehicle ever built to carry humans, faster than any airplane, faster than any bullet. And yet, even at that incredible speed, Voyager would need more than 70,000 years to reach the nearest star. 70,000 years. That is longer than the entire history of human civilization. But Voyager's journey reveals something even more unsettling. Not just how far away the stars are, but how empty the space between them really is. Inside the solar system, the space between planets already feels vast. But beyond Neptune, the emptiness becomes extreme. Just past the orbit of Neptune lies a region known as the Kuiper Belt, a vast ring of icy objects left over from the formation of the solar system. Some of these bodies are hundreds of kilometers across. others are only a few kilometers wide. Pluto lives here. So do thousands of smaller frozen worlds. The Kuiper Belt stretches from about 30 astronomical units to 50 astronomical units from the Sun. That means its outer edge lies roughly 7.5 billion kilometers away. But even this is not the edge of the solar system. Not even close. Far beyond the Kuiper Belt lies something far stranger. A structure so distant that no spacecraft has ever reached it. A gigantic spherical cloud of frozen debris surrounding the Sun in every direction. Astronomers call it the Oort cloud, and visual, solar system surrounded by distant spherical cloud. The inner edge of the Oort cloud may begin around 2,000 astronomical units from the Sun. That is 300 billion kilometers, but the outer boundary could extend as far as 100,000 astronomical units. At that distance, the Sun's gravitational influence stretches nearly 1.6 light-years into space. One star's gravitational territory, stretching across a region almost 2 light-years wide. Now remember Voyager 1, our fastest outward traveler. After nearly 50 years, Voyager has reached a distance of about 160 astronomical units from the Sun. That means it has not even entered the Oort cloud yet. Not really. It is still wandering through the inner outskirts of our own solar system. And at its current speed, Voyager will need roughly 300 years just to reach the inner edge of the Oort cloud. To cross the entire cloud could take tens of thousands of years. All of this distance, all of this emptiness, and we have not even reached the nearest star. Visual, camera pulling away from solar system into interstellar darkness. Because outside the Sun's gravitational domain lies something even more extreme. The true void between stars. Interstellar space. A region so empty that calling it space almost feels inadequate. In the air around you right now, each cubic centimeter contains about 25 quintillion molecules. In interstellar space, the average density is roughly 1 atom per cubic centimeter. 1 atom, not 1 molecule. 1 atom. The emptiness is almost absolute. And yet even this emptiness is not completely safe, because scattered through the darkness are high-energy particles, cosmic rays, microscopic dust grains, atoms accelerated by distant supernova explosions. For a spacecraft moving slowly, like Voyager, these particles are mostly harmless. But if a spacecraft were ever to travel at a significant fraction of the speed of light, those tiny particles would become deadly. Each collision would strike the spacecraft with the energy of a microscopic explosion. Space is not just empty. It is hostile, but the most unsettling realization comes when we look at the distance between stars. The nearest star system to our Sun is Proxima Centauri. Its distance? About 4.24 light-years. That means light, moving at 300,000 kilometers per second, still needs more than 4 years to get there. For Voyager 1, the journey would take about 73,000 years, and that is just the nearest star. Within our galaxy, the stars are separated by distances that make the solar system look microscopic, which leads to the next step in this journey. Because everything we have measured so far, Earth, the Sun, the solar system, the Oort cloud, Voyager, the nearest stars, all of it exists inside something far larger, a structure so enormous that the entire solar system disappears inside it. A structure containing hundreds of billions of stars, our home galaxy, the Milky Way. And once we see its true size, the solar system will vanish completely. If you're enjoying this journey through cosmic scale, you're exactly where you should be. Here on If Earth Had a Past, yet we explore the hidden history of the universe and the astonishing structures that shape it. And we are only getting started. Everything we have measured so far feels enormous. The size of Earth, the power of the Sun, the distances between planets, the emptiness stretching beyond Neptune. All of it seems unimaginably large. But in the next step of our journey, something extraordinary happens. Everything we just measured disappears. It's visual, solar system shrinking rapidly. Imagine compressing the entire solar system into something small enough to hold in your hand. Shrink the sun down to the size of a large grapefruit, about 20 centimeters across. At that scale, Earth becomes a tiny pebble, barely 2 millimeters wide. That pebble would orbit the grapefruit at a distance of roughly 23 meters, about the length of a school bus. Mars would be slightly farther out. A Jupiter, the giant of our planetary family, would appear as a ball roughly the size of a large orange, about 120 meters away. Saturn would sit nearly 220 meters from the grapefruit sun. And Neptune? Neptune would be almost 700 meters away, nearly half a mile from the front door. In this scale model, the solar system becomes something the size of a small neighborhood, but almost every meter of that neighborhood is empty. No planets, no objects, just empty space between a handful of scattered spheres. But now comes the unsettling part, because this entire model, the sun, the planets, the half-mile solar system, is still only one tiny piece of a far larger structure, a galaxy. Visual, camera zooming out from solar system into star field. The Milky Way galaxy is the vast stellar system that contains our sun and everything gravitationally bound to it. Seen from above, it would look like a gigantic spiral. Long, curved arms of stars, gas, and dust swirling outward from a bright central core. Astronomers classify it as a barred spiral galaxy. The central region contains a dense bar of older stars. From that bar extend several sweeping spiral arms. Our solar system lives inside one of the smaller structures called the Orion Spur, located between two major spiral arms. We are not near the center of the galaxy, and we are not near the edge. We live somewhere in the quiet suburbs, about 26,000 light-years from the galactic core. To understand the scale of the Milky Way, we have to abandon kilometers and miles entirely. The numbers become too large to be useful. Instead, astronomers use a different unit. The light year. A light year is the distance light travels in 1 year. Since light moves at about 300,000 kilometers per second, a 1 light year equals roughly 9.46 trillion kilometers, about 5.88 trillion miles. Even that number is difficult to grasp, but it gives us a way to measure the enormous distances between stars. The Milky Way galaxy stretches across about 100,000 light-years. That means a beam of light leaving one edge of the galaxy would require 100,000 years to reach the opposite side. 100,000 years. For comparison, Homo sapiens has existed for roughly 300,000 years, which means light needs about 1/3 of the entire history of our species just across our galaxy. And inside that immense disk of stars, astronomers estimate the Milky Way contains somewhere between 200 billion and 400 billion stars. Each one a sun. Each one potentially surrounded by its own system of planets. Recent observations suggest our galaxy may contain more than 100 billion planets. Some estimates push that number closer to 300 billion. Entire worlds. And entire solar systems, scattered across a structure so large that the solar system becomes invisible within it. To visualize this scale, imagine standing at the 50-yard line of an American football field. Now place a single grain of rice at your feet. That grain of rice represents the entire solar system, every planet, every moon, every asteroid, every spacecraft humanity has ever launched, all of it compressed into one tiny grain. And now ask yourself how large the Milky Way would be at this scale. Not the football field, not the stadium, not even the city surrounding it. At this scale, the Milky Way would stretch far beyond the city limits. The solar system would be almost impossible to find. You could search the entire stadium with a magnifying glass and still struggle to locate that grain of rice. That is how small our cosmic neighborhood is compared to the galaxy that contains it. But the scale becomes even stranger when we consider motion. Because our sun is not standing still inside the Milky Way. It is orbiting the galactic center. Visual, solar system orbiting galaxy. The sun travels around the center of the Milky Way at about 828,000 kilometers per hour, roughly 515,000 miles per hour. An incredible speed, faster than any spacecraft humanity has ever built. Yet even at that speed, one complete orbit around the galaxy takes about 230 million years. Astronomers sometimes call this a galactic year. The last time the sun was in this exact position within the Milky Way, Earth looked very different. Dinosaurs had just begun to appear. The supercontinent Pangaea was still largely intact. There were no birds, no flowering plants, no humans. Our star has completed only about 20 galactic orbits since the solar system formed. 20 revolutions around the galaxy in 4.6 billion years. Now imagine looking at the Milky Way from far outside it. From a vantage point, millions of light years away. What would our solar system look like? Nothing. Not even a dot. Even the sun would blend into the glow of billions of other stars. To find it would be like standing in the middle of a dark city filled with 400 billion fireflies and trying to identify one specific firefly. One that is not particularly bright, not particularly large, and located in a completely ordinary part of the city. You would never find it. Not in 1,000 lifetimes. That is how deeply hidden our solar system is within the Milky Way. But the Milky Way itself, as vast as it seems, is not the largest structure in our neighborhood. Not even close. Because just outside the borders of our galaxy, there exists another one, larger, brighter, containing far more stars. A galaxy visible from Earth with nothing more than the naked eye. Visual, faint smudge appearing in night sky. On a dark autumn night, far away from city lights, you can see a faint smudge in the constellation Andromeda. It looks like a tiny blur, almost like a distant cloud. For centuries, astronomers believed it was a nebula inside our own galaxy, a small patch of glowing gas. But in the early 20th century, that assumption collapsed. And when scientists finally measured the true distance to that faint smudge in the sky, the size of the universe expanded overnight. Because that smudge was not a cloud. It was another galaxy, an island of stars, floating in the darkness beyond the Milky Way. And once we measure its true size, the Milky Way itself will start to feel small. If you're fascinated by these cosmic journeys through space and time, you're in the right place. Here, on If Earth Had a Past, while we explore the deepest history of the universe and the astonishing structures hidden within it. And the next one we're about to encounter is bigger than everything we have seen so far. For most of human history, the universe seemed relatively small. Ancient astronomers believed the stars were fixed lights embedded in a cosmic sphere surrounding Earth. Later, as telescopes improved, scientists discovered that our solar system was only one small part of a much larger structure, the Milky Way galaxy. By the early 1900s, many astronomers believed the Milky Way was the entire universe. Everything that existed inside this single galaxy. But scattered across the night sky were strange objects, faint, cloudy shapes visible through telescopes. Astronomers called them spiral nebulae. They appeared as small swirls of light, beautiful, mysterious. And nobody knew what they were. Visual, old telescope image of Andromeda Nebula. Some scientists believed these spiral nebula were simply gas clouds inside the Milky Way. Others suspected something far more radical, They proposed that these objects might be entire galaxies of their own, enormous systems of stars located far beyond the boundaries of our galaxy. Separate island universes. The disagreement became one of the most famous scientific arguments in astronomy. It was called the Great Debate, and for years neither side could prove their case, because the distances involved were simply too large to measure with the instruments available at the time. Until one astronomer looked closer. Visual, Mount Wilson Observatory Telescope. In the early 1920s, astronomer Edwin Hubble began observing the Andromeda Nebula using the 100-inch Hooker telescope at Mount Wilson Observatory in California. At the time, as it was the most powerful telescope on Earth. Night after night, Hubble exposed photographic plates of Andromeda, long exposures that captured light too faint for the human eye to see. When he studied the plates carefully, something extraordinary appeared. Tiny points of light inside the nebula, individual stars. Not gas clouds, stars. And among those stars, Hubble identified a special kind of object known as a Cepheid variable, visual Cepheid star pulsating. Cepheid variables are stars whose brightness changes in a predictable cycle. They pulse, bright, dim, bright again. And years earlier, astronomer Henrietta Swan Leavitt had discovered something remarkable about them. The speed of a Cepheid's pulse is directly related to its true brightness. A slowly pulsing Cepheid is genuinely brighter than a rapidly pulsing one. This discovery gave astronomers a powerful tool. But if you measure how quickly a Cepheid pulses, you can determine how bright it really is. Then you compare that true brightness with how bright the star appears from Earth. From that difference, you can calculate its distance. For the first time in history, astronomers had a cosmic measuring tape. Hubble applied this method to the Cepheid variable he had found inside Andromeda. He measured its pulsation period, calculated its true luminosity, compared it to its faint appearance in the telescope, and the result stunned the astronomical community. The star was unbelievably far away, far beyond the outer edge of the Milky Way. And if that star was inside the Andromeda Nebula, then the nebula itself had to be even farther, which meant Andromeda was not inside our galaxy at all. It was a completely separate galaxy, an island of stars floating millions of light years away. When Hubble announced his findings in 1924, the scale of the known universe exploded overnight. Before that moment, astronomers believed the universe consisted of one galaxy. Now they knew there were at least two. And if one spiral nebula turned out to be another galaxy, then perhaps many of them were. The universe suddenly became vastly larger than anyone had imagined. Oh, visual, Hubble marking VAR on photographic plate. One famous detail from that discovery survives today. On the photographic plate where Hubble identified the Cepheid variable, he wrote a small note beside the star. Just 3 letters. VAR, short for variable star. Those 3 letters marked one of the most important discoveries in the history of science, because they proved that the faint smudge in the constellation Andromeda was not a cloud. It was a galaxy. And not just any galaxy. One of the largest galaxies in our entire cosmic neighborhood. Visual, Andromeda Galaxy slowly appearing in full. The Andromeda Galaxy, also known as Messier 31, lies about 2.5 million light-years away from Earth. It is the most distant object visible to the naked human eye. On a dark night, far from city lights, you can actually see it, a faint patch of light in the sky. But that faint glow is not a small object. It is the combined light of roughly 1 trillion stars. 1 trillion. For comparison, the Milky Way contains about 200 to 400 billion stars. That means Andromeda may contain 2 to 5 times as many stars as our galaxy. Its disk stretches across roughly 220,000 light-years, more than twice the diameter of the Milky Way. Its central black hole is about 100 million times the mass of the Sun, 25 times more massive than the black hole at the center of our galaxy. And Andromeda commands an entire family of smaller satellite galaxies orbiting around it. Dozens of them, all bound together by gravity. But the most astonishing detail about Andromeda is not just its size, it is its motion. Because the Andromeda Galaxy is not drifting away from us, it is moving toward us. Visual: Andromeda slowly approaching Milky Way. Astronomers can measure the motion of galaxies using a phenomenon called redshift and blueshift. When an object moves away from us, its light stretches toward longer wavelengths, shifting toward red. When it moves toward us, the wavelengths compress, shifting toward blue. And the light from Andromeda shows a clear blue shift. The galaxy is approaching. At a speed of about 110 kilometers per second, that's roughly 400,000 kilometers per hour, about 250,000 miles per hour. Two giant galaxies, each containing hundreds of billions to a trillion stars, thus separated by 2.5 million light-years of space, and slowly, inevitably, moving toward each other. But before we talk about the collision that will one day reshape both galaxies, we need to understand the distance between them. Because that distance, 2.5 million light-years, is where the human mind finally reaches its limit. If exploring the deepest structures of the cosmos fascinates you, you're exactly where you belong. Here on If Earth Had a Past, we journey through the hidden history of the universe, one scale at a time. And the distance we're about to measure next is one of the most difficult numbers the human brain will ever attempt to understand. We now arrive at the number that has been quietly waiting behind this entire story. The distance between our galaxy and the Andromeda Galaxy. About 2.5 million light-years. It is a number that sounds simple when spoken. But the moment we try to understand it, something strange happens. Numbers stop behaving like numbers, and the human brain begins to fail. Let's start with a single light-year. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, roughly 186,000 miles per second. At that speed, light circles Earth 7 times in 1 second, and yet even light needs time to cross the vast distances of space. In 1 year, a light travels about 9.46 trillion kilometers, or 5.88 trillion miles. That is 1 light-year. Already far beyond anything humans have ever traveled. The farthest any human has ever been from Earth is the distance to the Moon. During the Apollo missions, astronauts reached about 384,000 kilometers away. That journey represented the greatest physical distance humans have ever crossed. But 1 light-year is about 25 million times farther than the Moon. 25 million. Every rocket ever launched, every spacecraft ever built, every human journey into space combined does not reach even a tiny fraction of 1 light-year. Now multiply that distance by 2.5 million. That is the gap between the Milky Way and the Andromeda Galaxy. In kilometers, it equals roughly 23 quintillion 650 quadrillion kilometers, or about 14.7 quadrillion miles. Numbers that large no longer create images in our minds. They become abstract. So instead, let's translate that distance into time. Light, the fastest thing in the universe, needs 2.5 million years to travel from Andromeda to Earth, which means the light entering your eyes tonight left that galaxy 2.5 million years ago. 2.5 million years. At that time on Earth, modern humans did not exist. The genus Homo had not yet appeared. Our distant ancestors were early hominins like Australopithecus, walking upright across the African savanna with brains much smaller than ours. No cities, no tools of metal, no agriculture, no writing, no telescopes. The photons reaching your eyes tonight began their journey long before any human civilization existed. They traveled through darkness for millions of years, across the enormous void between galaxies. And their journey ends in a tiny patch of cells on the surface of your retina, converted into electrical signals by a brain that weighs about 1.4 kilograms and runs on roughly 20 watts of power. But the most astonishing detail about this distance is not just its size, it's what fills it, or more precisely, what doesn't. Between the Milky Way and Andromeda lies intergalactic space, one of the emptiest environments in the known universe. The average density of matter there is roughly 1 atom per cubic meter. 1 atom. As inside a space the size of a large cardboard box, you would likely find nothing at all. For comparison, the air around you right now contains about 10 to the 25th power molecules per cubic meter. The difference between air and intergalactic space is so extreme that laboratory vacuums on Earth cannot even approach it. Intergalactic space is emptier than anything humans can create. Here is a way to visualize that emptiness. Imagine a swimming pool filled with perfectly pure water. And now imagine removing every molecule of water from that pool, except for a single grain of dissolved salt. That pool would still contain more matter per unit volume than the intergalactic void between the Milky Way and Andromeda. This is the space separating the two largest galaxies in our local cosmic neighborhood. A gulf of almost perfect nothingness stretching 2.5 million light-years in every direction. And across that void, something remarkable is happening. The Andromeda Galaxy is moving toward us. Not quickly in human terms, but steadily, inevitably. Astronomers measure this motion using the Doppler shift of light. When a galaxy moves toward us, its light shifts slightly toward the blue end of the spectrum. Andromeda's light is clearly blue-shifted, which means the galaxy is approaching at about 110 kilometers per second. That's roughly 400,000 kilometers per hour. Every single year, Andromeda moves about 3.5 billion kilometers closer to the Milky Way. The gap between the galaxies is shrinking, slowly, silently, across millions of years. But don't worry, this approach is happening on timescales far beyond human history. At the current rate, the first close encounter between the two galaxies will not occur for about 4 to 5 billion years, roughly the remaining lifetime of our Sun. Civilizations will rise and fall. A species will evolve and disappear. Entire continents may shift across Earth's surface, long before the galaxies finally meet. Yet the approach is real. 2 enormous spiral galaxies, each containing hundreds of billions of stars, each surrounded by massive halos of dark matter, slowly moving toward each other through the deepest emptiness in the universe. And when they finally meet, something extraordinary will happen. Because a collision between galaxies does not look like anything we experience on Earth, stars will not crash together. Planets will not explode. Instead, the encounter will unfold as a vast gravitational dance lasting hundreds of millions of years. Spiral arms will stretch and twist. Stars will be flung into new orbits. New stars will ignite as clouds of gas collide and compress. And eventually, the two galaxies will merge into a single enormous system. A galaxy sometimes nicknamed Milkomeda, a structure containing perhaps 2 trillion stars. But before we reach that future, there is one final question left in this journey. A question that every civilization must eventually ask. Now that we understand the scale of the universe, could we ever cross it? Could humanity, or any civilization, travel the 2.5 million light-years separating us from Andromeda? Or is that distance something no biological species will ever overcome? Because the answer to that question reveals something profound about the universe we live in, and about the limits of any civilization that evolves inside it. If journeys like this fascinate you, this is exactly what we explore here on If Earth Had a Past. But the final step of this story may be the most unsettling one yet, because the universe allows us to see distant galaxies, to measure them, and to understand them, but it may never allow us to reach them. Now we arrive at the final question. After measuring the Earth, the solar system, the Milky Way, and the enormous distance to the Andromeda Galaxy, one question remains. Could we ever go there? Could any civilization travel the 2.5 million light-years between our galaxy and the next one? The answer begins with something simple. Speed. Humanity has already launched spacecraft beyond the planets. The fastest human-made object ever sent into deep space is Voyager 1. It travels at about 17 kilometers per second. That's roughly 61,000 kilometers per hour. About 38,000 miles per hour. An astonishing speed by human standards. But against the scale of the universe, it is almost nothing. At Voyager's speed, reaching the Andromeda Galaxy would take about 44 billion years. 44 billion. For comparison, the entire universe is about 13.8 billion years old. Even if Voyager had launched at the moment of the Big Bang, it still would not have reached Andromeda by now. It would still have tens of billions of years left to travel. Perhaps a faster spacecraft could solve the problem. Imagine a future civilization capable of building a ship that travels at 10% of the speed of light. That is about 30,000 kilometers per second, nearly 2,000 times faster than Voyager. At that speed, the journey to Andromeda would take roughly 25 million years. 25 million years. When that journey began, Earth was home to early ancestors of modern apes. The entire evolutionary path from those primates to modern humans fits inside that travel time. No human civilization has lasted anywhere near that long. Maybe we push the speed even further. Imagine a spacecraft capable of traveling at 50% of the speed of light, an almost unimaginable velocity requiring energy on a colossal scale. Even then, the journey to Andromeda would still take about 5 million years. 5 million years ago on Earth, our ancestors had only just begun walking upright. Everything that defines human civilization, language, culture, science, technology, happened within that window of time. There is one final possibility: travel at speeds extremely close to the speed of light. At 99% of light speed, and Einstein's theory of relativity begins to change how time behaves. For travelers moving that fast, time slows down relative to the outside universe. From the perspective of the crew, the journey might feel much shorter, perhaps only a few decades of experienced time. But outside the spacecraft, the universe would still age by 2.5 million years. Everyone who launched the mission would be separated forever from the civilization that sent them. When they arrived, the Milky Way they left behind would be ancient history, and the Andromeda Galaxy they aimed for would have changed as well. Stars would have moved. New stars would have formed. Others would have exploded as supernovae. The galaxy they studied before departure would no longer exist in the same form. They would arrive in the distant future of a galaxy that had evolved beyond recognition. And even this scenario hides enormous obstacles. Accelerating a spacecraft to 99% of the speed of light requires energy comparable to the output of entire stars. Shielding a vessel traveling that fast from microscopic dust particles becomes a serious engineering challenge. A tiny grain of dust at that velocity would strike with the energy of an explosion. The deeper we examine the physics, the clearer the conclusion becomes. Intergalactic travel may simply be beyond the reach of biological civilizations, but not because we lack intelligence, but because the architecture of the universe itself places limits on what is physically possible. Within our own galaxy, exploration might eventually be achievable. Even at 10% of the speed of light, a civilization could spread across the Milky Way over millions of years, colonizing star systems, exploring billions of planets, building a vast network of worlds across the galaxy. The Milky Way alone contains hundreds of billions of stars, more than enough destinations for any civilization that might emerge here. But the leap from interstellar travel to intergalactic travel is something entirely different. The distance to Andromeda is 25 times larger than the diameter of the Milky Way itself. And between those galaxies lies almost nothing. No stars, no resources, no stepping stones. Just an ocean of emptiness stretching for millions of light years. And yet, despite that distance, you can still see Andromeda. Visual. Andromeda Galaxy glowing in night sky. On a clear night, under dark skies, the Andromeda Galaxy appears as a faint smudge of light, tiny, almost invisible. But that faint glow is the combined light of 1 trillion stars, each one a sun, many with planets of their own, worlds that may have oceans, atmospheres, possibly even life. All of it contained inside a galaxy 220,000 light-years across, drifting silently through the darkness and slowly moving toward us. You may never travel there. No human likely ever will. But something remarkable happened on this small planet orbiting an ordinary star. A species evolved capable of understanding the universe around it. A species that could measure galaxies millions of light years away, calculate their motion, estimate their mass, predict their future, all from the surface of a world only 12,742 kilometers wide, using a brain that weighs about 3 pounds and consumes the energy of a small light bulb. The universe is unimaginably vast. The distances between its islands of stars may forever separate them from one another. But the fact that we can see them, measure them, and understand them is extraordinary. Across millions of light years of darkness, the universe has revealed its scale to us, and in doing so, it has revealed something about ourselves as well. We may be small, but we are capable of understanding something far larger than ourselves. And that may be one of the most remarkable things the universe has ever produced. If journeys through the deep history of the cosmos fascinate you, this is exactly what we explore here on If Earth Had a Past. Because every planet, every star, and every galaxy has a story, and we are only beginning to uncover it.